In this joint Capstone project with ASU Fulton School of Engineering and Collins Aerospace, we have worked to redesign an evacuation slide aspirator for aircraft. But what is an aspirator? Some aspirators from everyday life can be seen in perfume spritzers or in the airbags of automobiles. Others can be seen in natural occurrences, such as the airflow between city buildings, and the air shafts in mines and caves that cycle the air from the entrance and out the top of the shaft of the hill or mountain. The evacuation slide aspirator sits between the folded slide and a pressurized tank. Upon activation, the regulated tank pumps high-pressured gas into the aspirator. This starts a vacuum effect that sucks outside or ambient air into the slide and inflating it. The mechanical function behind the workings of an aspirator is known as the Venturi effect. This effect takes place when a high pressure and low velocity gas or liquid enters a low pressure and high velocity choke point. The flow then enters another high pressure and low velocity zone. The pressurized gas inlet at the choke of the aspirator allows the system to have a lower pressure and higher velocity at this point. As a result, the aspirator can pull more ambient air and keep the vacuum flowing. In this project's aspirator redesign, we inverted the entry point of the pressurized gas, or primary flow, into the aspirator funnel. The base aspirator model provided by Collins Aerospace had the primary gas flow in the center of the funnel, and the ambient air, or secondary flow, pulling past it. In our design, we instead have the primary flow entering around the walls of the aspirator, clearing the way for the ambient air down the center of the funnel. Other than this design change, the redesign reduced size, weight, and cost of the aspirator, as well as reducing the part count and complexity of manufacturing. The many design iterations in this project work toward optimizing the flow ratio of parts ambient air to parts pressurized gas, or otherwise known as the entrainment efficiency of the aspirator. With each iteration, the aspirator's inner profile and geometries were changed based on Collins' expert feedback and tested using conceptual fluid dynamics, or CFD. All of this was in hopes of designing a model that obtained an entrainment efficiency near 3 parts ambient air to 1 part pressurized gas. By the end of the design process, our virtual aspirator prototype held an acceptable entrainment efficiency and provides a new evacuation slide aspirator to the world of aircraft safety.